All right, I think we should make a start.
Okay.
Just a reminder that this is being recorded and will be posted on YouTube, hopefully today, if not tomorrow. This morning, we're going to hand over to Sebash, who's going to give us a bit of a chat on embedded systems.
Sensors and
Sensors.
energy harvesting.
Yeah. So I'll hand over to him, and then afterwards, if you've got questions, please ask. A bit of a discussion on how things are going. All right, so I'll hand over to Sebash.
Okay.
All yours.
Hi everyone. Good morning, good night, good evening, and all that. So let's get into it. This is our third seminars. Before we get started on today's topic, just a couple of quick reminders. As Ian mentioned, the video is going to be recorded. We're going to be posting the link on the edX channel. If you haven't received an answer to your email, please feel free to send that to us again. If you don't receive an answer within 2-3 days, feel free to just reply back to the message so it bumps up in our mailbox. We have one of your assignments due this Sunday. So this is the IoT presentation video. And a couple of people have been asking with this video, it can be you just talking, it can be a PowerPoint presentation. So we're a bit more flexible on the format of this one. And I'll show you the mark breakdown that we have for this assignment. And then the next one after that is the market research and costing plan, which is due on 30th of May. And if you've missed it, the last seminar that we had, Ian went into a deep discussion about the different points that you would include in this report. And one more thing I was going to add with the Canvanizers. Unfortunately, we've been a bit busy, but you should have your marks in about a week or so, and with our feedback. So this is a mark breakdown for your presentation. So this is going to be 15% of your marks. You're going to be marked on your IoT idea and unique value proposition, the problem that your IoT idea solves, a brief explanation of how that idea solves the problem, your potential customers, your business model, a summary, and the overall effectiveness of the presentation. Something interesting that we've seen in past videos is people have been trying to kind of model it off Kickstarter and Indiegogo pitch presentations. Those could be interesting to watch a couple of those sort of videos to get an idea how you would go about pitching an idea that hasn't really finished, but it's still in the idea stage. And this is the breakdown of the market research. And as I mentioned, we did have a discussion about this in the previous seminar, so make sure to watch that. And you're going to be marked on industry analysis, competitor analysis, product and services, pricing, and your SWOT analysis. Now, from now on, this MOOC is slightly different than other MOOCs because, as you've seen so far, there is a more direct interaction with us as academics and as, I guess, education providers. So now that we're done with some of the basic topics that we wanted to cover, from now on, each week we'll cover a topic of interest. So this week I'll be talking about sensors, a bit about signal processing and energy harvesting. And next week, Ian will talk about construction of prototypes and PCB manufacturing. And we have talks coming up from Hannes. I think we have talks coming up from David and Valerie. So on spatial sciences and a bit about algorithms and Valerie's area of expertise. So the last 2 weeks of the course, we're going to be running it for 2 extra weeks to give us time to actually go through the reports and mark them and give you feedback. So that's why we have 2 extra weeks running rather than the 12 weeks. All right, so let's get into it. I'm going to give you a very quick overview of sensors, and I'll try to keep this brief so we can have a discussion about the sensors afterwards. And if you have any questions, looking for advice, looking for choosing your platform, this would be the best place to ask for that. So as a quick overview, many systems require measurement or detection of a particular condition, so whether it's physical, chemical, or electrical. And these detectors that we have in these systems are often used as on and off switches that look at the presence of a signal or an environmental condition. So these analog sensors that we have, they indicate the magnitude of change in environmental condition by means and value of a change in electrical characteristic or property. So the usual electrical magnitudes include voltage, current, resistance, capacitance, Hall effect, and charge. So what this means is based on the type of sensor that we have, we would actually most of the time measure an electrical characteristic and then look at a data sheet and convert that electrical characteristic to an actual real life value. So based on what electrical characteristic the sensor is monitoring, we can divide sensors to active sensors and passive sensors. So if they're monitoring a current or voltage in response to environment stimulation, these would be active sensors, or like thermocouples, piezoelectric, and accelerometers. And the magnitude of the generator signal is usually quite small, so we need amplification. And we have passive sensors, where they produce a change in some passive quantity, like resistance and capacitance, or inductance, like thermoresistors, thermistors, and capacitive humidity. And in most cases, these types of sensors require power sources, but it's not the case for all of them. And usually the actual reading or proceeding from these types of sensors is by means of a voltage or by means of a value. So let's take a look at a couple of popular sensors. This is something that I like. This is a FSR, or force sensitive resistor. Basically, this is how you would connect it to a very simple Arduino. And when you apply pressure on it, it will change the resistance. And we can use this to detect pressure. We can use this to as a state change in a very simple program. And as you can see, the code for it, and this is just a very simple Arduino code, we're just basically reading the pin that's connected to the FSR and then printing the values. Another one that we have here as an example is the TMP36. It's a very simple temperature sensor. As you remember, I mentioned with sensors, we usually calculate a change in an electrical characteristic and then convert it to actual values. So in this case, this TMP will give you a change in voltage, and then we convert that to actual temperature using this equation. Excuse me. So what you see here, where I would get this typical equation, this would be in the data sheet of the sensor. And this is a very simple way of connecting, oops, went back. This is a very simple way of connecting that sensor to our Arduino. So it has a voltage pin, ground pin, and what we call a signal pin. And the signal pin is what we're reading to convert to actual values. So if you look at this simple code for it, you can see that we are reading the pin that's connected to the sensor. And over here, this is where we are actually changing the reading value to actual temperature. And we also have the centigrade and Fahrenheit to display that information. Okay. Okay, sorry, bit of technical difficulty here. Now, let's move on to my favorite sensors, IMUs, or initial measurement units. So these sensors, what we have in them, we have an accelerometer, magnetometer, and a gyroscope. And each of these different sensors will give us different values. So accelerometer will give you linear acceleration, magnetometer measures the magnetic field, and gyroscope is used to maintain orientation. So what we do with these sensors, there are many uses for them. But one of the best use cases that we have from them is we fuse this sensor information together. So we fuse the accelerometer, magnetometer, and gyroscope data together to get an orientation of an object. Now, this orientation can be a simple representation in Euler angles, which give you pitch, roll, and yaw. So if you imagine this plane in the 3D space, and interesting enough about this image, if you see any IMU paper or article, you're going to see this image used because it's a very good representation of what pitch, roll, and yaw are. And this is just a free open source image in an article. But anyway, basically, it gives you the object's orientation in the space. So we can tell what the object is doing without needing to have a camera. So we can get that orientation. There's another way of using IMU data, which is quaternion. I haven't brought it here because it's a bit more complex. To put it very simply, it gives you the probability of the object's position in the space. So it uses 4 imaginary values. And gives you that representation. But with Euler angles, we have the pitch, roll, and yaw as 3 values that that can be provided for us. So they have very interesting use cases, and I'll show you a couple of examples of them. But we use them to track human movement. We use them to track dog movement. We use them to track, and this is what quadcopters and UAVs usually have in there to maintain their orientation in the air. So they're very useful. And we've also have experience with using it to track how fast someone is throwing the ball, someone's heading a ball. So lots of interesting applications. But before we get to examples, let's talk a bit about signal conditioning, which is manipulating the signals that you get directly from the sensor to make them a bit more readable. The 3 main points are linearization, amplification, and filtering. With linearization, we can see an example of it where we have a signal that's not linear and we wanted to have a linear representation of it. So hence the word linearization. Amplification, as we mentioned in the case of some active signals, we need to amplify the output so the changes can be a bit more visible. And one of the more crucial ones is filtering, where you can see some before and after effects of a filter on a signal, where we want to either filter out the noise or the unrequired values from a signal, or imagine we have a movement data from a couple of different things like walking, then going up and down a stair, then falling down, and we wanted to filter out each of these individual events. So that would be another use of filtering. Now, let's take a look at some a sensor, IMU, and kind of package type projects. This is something actually my wife's working on as well. This is tracking white cane movement for vision impaired people. And the idea is we want to remotely track that white cane movement to be able to tell the vision impaired people how they're using the white cane and if they're using it correctly or not. This is a prototype. As you can see, it's literally sticky tape together. So I like to call this the sticky tape prototype. We were using an Arduino Pro Mini and a 9150 IMU and a Bluetooth module and a battery on the transmitter. And then there was a Arduino and a transceiver on the other end as the receiver. And this is how it looked like. So we had one IMU connected to the white cane, one connected to one of the legs, because when we started initially, we had more IMUs, but it turned out that we can, based on the correlation that's between the 2 legs, we could just determine where the second leg would be positioned based on the first one. So here's a video that we have, I want to show you here. Now, this is someone using the white cane, one of my students, and we've synchronized it so we can see what's happening in the video and in the signal. Now, it's interesting to see, and this is where we usually start our analysis. We would take a video and we'll try to see what was happening in real life versus what's happening with the sensor data. So this is simply the Euler angles of the white cane at the bottom and the leg at the top. So you see these parts of the signal. Let me turn on this laser pointer. So these parts of the signal, these are the turns that the person took when he was going through the hallway. So if I play the video back again. See? So that's what happened. Another similar project that we did in this vein was the same idea, but this time tracking walking guide dog movement. And the idea behind that project, which is here, and I'll play the video in a sec, is we have sensors and a 360 camera connected to this handle, and all of the dog information and sensor information will be transmitted to a base station where the trainer would put on a VR headset and guide someone to go to a new pathway. Because as it stands, if a blind person wants to go to, say, a new shopping center, you have to get a trainer to go with them on that path and multiple times, have them memorize the path, help the dog memorize the path, and then use it. And especially, it's going to be especially difficult if that person is living in a remote area, right? So our idea was to do this remotely. So here's a video. And and we have the visual representation of the harness, as you can see at the bottom left of the screen, as it's moving. And at this stage, we're trying to distinguish between the front leg and back leg movement of this dog to see what we can do with it, basically, then help determine if there are any signs of lameness and limping that's happening. So this would be interesting. And all we're using, so you see that tiny sensor you see at the top of the harness, there's this tiny orange sensor that's in the middle. That is a single IMU that we're using to capture that information. So let's move on. And another project that we have, so more looking at human movement. Again, I wanted to show you this project starting as a kind of sticky taped prototype where we took an Arduino Pro Mini and made a small version of that. And again, sticky taped it to the breakout board for an IMU and an infrared sensor as a transmitter device. Then we had the receiver here, where we had the Arduino Uno connected to a transceiver. If you can literally see the sticky tape coming out. And the idea is we would start from this sticky tape solution as a prototype, run some experiments, and once we're sure all of the devices work together, that's where we would go and design a PCB. So this is an ongoing one that we're looking at this stage, where I'm getting the actual IMU and making sure all of the other components fit on the same IMU. This project, the purpose of it was to use two of these sensors on the hand, so on the back of the hand and slightly above the wrist, to try to track the movement of children with cerebral palsy. Because as it stands, and if you don't know what cerebral palsy is, it's basically a brain defect that can happen through birth, and it will lead to muscle spasms and difficulty, and people will have difficulty moving different muscles. So if you've seen people holding their hand at a very awkward angle, that could potentially be cerebral palsy. So because calculating that movement can be difficult, using what we call a goniometer, which is basically just two rulers that they put on top of the hand to capture that joint angle. We wanted to do that digitally. So that was the motivation behind this project. And this is actually part of my ongoing PhD research. So the way this setup worked, I would see a stream of data coming in. And if we were to purely look at some signals, I was running some tests, like looking at rapid hand movement. So starting slowly, then quickly moving my hand, so we can clearly see that in the signal. Where at the beginning, this is the slower hand, then moving forward, I'm moving it faster, because with this particular test, I was trying to find a maximum, minimum movement area for my sensor, so I can set up the scale for it. And another one, and as you can see on the z-axis, you see that the signal has drifted down. This is one of the problems with IMUs, because over time they drift down, especially when you're working with the hand, because hand is just in the air. You have one of the difficult problems with the hand movement is finding that initial position, whereas with walking, so with the dog or with the white cane, every time we take a step, And after a couple of steps, because it's a very well-defined value, we can use that to quickly recalibrate. Whereas when we are in the air, right, it's difficult at that as the sensor starts drifting. How do we solve for that? And this is the placement of the sensors that I was talking about. And a quick comparison video that you can, kind of image you can see here, having the normal hand movement on the left hand side, and then what the technical term would be, I guess, abnormal hand movement on the right hand side. Sorry, abnormal on the left and normal on the right, where you can see the maximum value for the peak of the signal for the cerebral palsy sample is about 25, whereas with the other one, it's close to 100. So that's how we can kind of determine there's going to be a difference between that hand movement. Now, another route that I've been kind of experimenting with was, because when I started my research, there weren't that much kind of affordable commercial solutions for something like this, where it would give me clean IMU signals. Then Xsense released their Xsense dot modules, where they give a pretty clean signal. And well, look, from an engineering electronic point of view, if you just look at the sensor and the equipment that's physically on the sensor itself, the cost of the parts is not that much, probably under $100. But the fact that you see something like this costing like 4 or 5 set of these sensors, they're about 500 euros, is the customer support that they provide, and it's their R&D costs that they spend to kind of develop these sensors and develop the algorithms for it. So a couple of things that I've done with this sensor that could be interesting. I've kind of started modeling a very simple hand movement by having 3 of these sensors connected. So I build this object, and then I'm attaching each of these sensors to one of these objects. This is a software that comes free with this sensor. And well, I thought, okay, that's an interesting idea. So let's take it outside a kind of a proprietary software and do something similar based on any IMUs that you can have. So I ended up working with one of my students and building a hand model in Unity. Basically, you see this one now. This is similar idea, a more accurate representation of the hand movement on a laptop, where the sensors are transmitting the information, and I'm reading the joint angle in real time, and I'm getting the orientation of the hand in real time. And you see the good marginal more at the top right, at the middle right of the screen. We were just putting some limits that we wanted to tell people, okay, if you're doing, say, a hand exercise, how close to an ideal point of movement you are and how far away you are. And we're kind of looking into kind of investigating further and implementing this as a telehealth, so we can remotely monitor hand movement. So if someone's under care of a physician, they don't have to come in every week for the physician to look at their movement. They can remotely do it. So if there's a problem, and if say they live far away from a medical facility. So as you can see, we can do lots of very interesting things with IMUs, from human movement, dog movement, white cane movement, and well, we're engineers, so I don't have that many sports applications to show you, but we started working on some smart applications, kind of hitting a ball and that sort of stuff. So moving forward, I wanted to give you an idea of where you would start working with sensors. One option could be to get a couple of sensors, get a microcontroller, start capturing information and play around with it. Another interesting idea would be starting with these sort of sensor solutions. So something like that. This is a simple link sensor from Texas Instruments, where they give you a bunch of sensors on a single device, and they provide the hardware and software as open source. So they usually have an application like this where you can capture and gather different sensor data, or this Nordic 52 Thingy, that's as it's called, where it has a bunch of different sensors and IMUs and motion trackers and things on top of it. And here's a closer look at an application for it. And the reason I'm suggesting these devices isn't to just use them in your solution, is you can get an idea from something like this. You can pick one of these and look at a couple of sensors that they have on it. And then this would be a good starting point to design your own PCB, because most of these companies, they would provide the hardware PCB layout as open hardware and open source designs. So you could start by looking at a completed design that has a bunch of things that you don't need and start taking those out of the design. Or, yes, Ian, you wanted to add
Just a
something?
quick point there, Sebastian.
Yeah.
Just so people are aware, either the next seminar or the one after, we haven't decided exactly when, we may do it next time. We'll be having a look at how we actually go from the devices, the prototyping devices that Sebastian is talking about here, and go through your own design process to build a custom solution. And that's normally done, as Sebastian's mentioned, to reduce the cost, make it more efficient, bring stuff in-house so you know exactly how things work. But we do have a bit of a chat on that and how to get to that stage. Either next fortnight or one after, might bring it forward.
Okay.
Sorry, I just thought I'd mention that.
Yeah,
like
definitely. And that's where we get into exactly how would you start designing, what are the options, how can you order these boards to be manufactured. You can order them with the parts on top of them. You can just order the PCB. So we'll cover all of that in our next seminar. Now, I'm gonna finish up these talks by having a quick chat about energy harvesting. So energy harvesting is driving energy from ambient and background energy sources, and this is used to extend the battery life of your devices. So these are free and clean energy around us, and they can be potentially converted to electric energy. Examples of these types of harvesting, we have solar powers, wind power, human motion, and radio frequency. So with existing energy harvesters, we have a couple of examples of them are PV cells, wind turbines, piezoelectric cantilevers for vibration, and electromagnetic generators for radio frequency. So let's dig just a little bit deeper down into each of these types of energy harvesting. So with solar energy, we have photovoltaic cells that can be used as energy harvesting modules. And it's a very popular and mature technology in both research and practice. Mainly the different sizes of the solar panels that we have offer, and we have from portable ones to big ones that we're using for houses, or ones that are put on backpacks for embedded systems. And you see this term embedded system showing up a couple of times here. Embedded system refers to an electronic solution, usually with a microcontroller and a couple of sensors, where a device is designed for a specific purpose. And usually with an embedded system, the idea is you wouldn't necessarily change or update the software that's on the solution. So think of your microwave ovens, kind of temperature control system, or a washing machine, or that, or even old generation of mobile phones where it was a dedicated kind of slab of technology rather than the smart devices that we have these days. But well, nowadays the lines between what is embedded system, what's not an embedded system is being blurred, because we have capabilities of very quickly providing firmware updates. But that is what an embedded system is, if you're not familiar with the term. Anyway, back to our topic. There are some factors that affect solar power, including shadow effects caused by the clouds and ambient temperature. We can affect the output voltage. We have wind energy harvesting, which is again another mature technology. We have a lot of wind farms around the world. As an example, near Stockholm and CA, we have about 5,000 modern wind turbines. The availability of wind energy is slightly less predictable compared to solar, and not all of the wind power can be captured due to the different conversion techniques that are used there. So the efficiency of the wind turbines depend on the actual wind speed. And then we have kinetic energy, like vibration, that can be harvested by micro power generators and become power sources for fitness bands, wristbands, and wireless portable types of sensors. So a couple of kind of common mechanism, we have the piezoelectric, electromagnetic, and electrostatic type of these harvesters. And because of the low frequency vibration and is used for these types of harvesting, there and such as human motion, it's only sufficient to generate extremely low power output. So they don't give us as big of a power output compared to like a solar or a wind type solution. And finally, we have a radio frequency, which is well,
A
it's
quick comment
from
on the previous one, if you don't mind, Savash.
Yep, sure.
Yep. To be the pedant I normally am, this is actually referred to as energy scavenging. Yes, it is harvesting energy, but it's because it's making use of other aspects which are not directly related to the device. So a really good example of this is a friend of mine in Sri Lanka wanted to monitor wild elephants. And they are a big problem in Sri Lanka. They come into villages, they destroy crops, they're quite dangerous, as you can imagine. But the problem is when you have a tracker on an elephant, particularly a wild elephant, you don't want to go out and capture it again just to change the batteries. So what he did is he used the electromagnetic energy scavenging so that as the elephant walked, the magnet within the coil rattled, which produced enough energy to recharge the, I'm not sure whether it's super cap or a battery, probably a super cap, and enabled the system to keep going. And that was a good sort of solution. I'm not quite sure how far we got with that, but they did try it out, and we tried it in Perth, and it worked really well because we didn't have any problem with elephants in Perth.
Great.
Slide aside there.
Yeah, I think they are still investigating that idea because I've seen a couple of honors projects over there popping up with
Yeah,
kind of
it's
similar ideas.
Malatar Rusinghi. He's the Executive Dean of International Studies over there. Anyway.
Interesting. Cool. Thanks for that interesting story, Ian. Radio frequency. So we have this broadcasted from billions of radio transmitters, including mobile phones, portable radios, mobile stations, and broadcast stations. And it's poised to serve as an energy source to low power devices, which make these products more stable. It supplies power to various kinds of wireless sensing nodes within a 24-hour operation. And the energy transmitted from the RSOs can be very high, but the problem is only a small amount of that can be scavenged to be used for our devices. So,
I'm going to interrupt.
Yep.
Do you mention your water meter energy scavenging using the mechanical energy of water flow in that water leak monitor? You mentioned that?
No, but we have an example of that one coming in.
Okay.
Yeah.
No,
no, that's okay. But when I get to those water kind of energy harvesting, I'll bring that up. So a couple of interesting projects I found around the web. This one, there was this guy that he wanted to charge his phone. He had an old iPhone, and whenever he went out for a jog and listened to music, it would lose power, and he didn't want to invest money in getting a new one. So he thought, okay, energy scavenging. He put a couple of these piezoelectric devices at the bottom of the shoe, and then got some of the parts from an old light bulb control setup, and then put a shoe inlay and a power bank here, as you can see, or started harvesting energy. And another one, we can see an example of energy harvesting in a typical hydroelectric generator. And Ian, do you want to talk about the RSC example while I catch my breath a bit?
Sorry, the water
RSC.
leakage?
Yep.
This is a project where we want to be able to measure water flow to premises, either industrial premises or homes, and track to see if there's a slow leak or a burst pipe and shut the water off to prevent catastrophic water damage happening. Now, the problem is that in Australia, our water meters tend to be out in the front yard, in the garden. They're not inside, so we can't connect them to power. And they also tend to be covered by walls around the property, plants. Mine at home is under a big rose bush. So again, you can't use solar power to keep them charged, or not reliably anyway. So what we're looking at doing is using the water flow that you get through the meter to run a small turbine, much like a miniature version of what we see on Oh, there it is. We've got one right here. And the spinning of the turbine from the water flow then provides the power we need to keep the device charged. So a really good example of energy scavenging. And these things are fairly common. They're really, really cheap. What were they? $10 or something?
Yeah, I think $10-15 or something like that.
Yep. And if it's successful, we'll be able to keep our devices running for 10 or 15 years within the water meter and watch for burst pipes. The device then communicates out to over the mesh network that the Water Corporation has, notifies both the user and the Water Corp that there is a burst pipe, and people can then take action. But additionally, and this is the nice thing about IoT, these sort of solutions can then be used to look at your water usage on a more immediate basis. So we can get a pattern of usage, how much water are you using? And in countries like Australia, where water is an extremely rare resource, and we have water restrictions pretty much every summer, where you can't water your garden, you'll be able to tell what your water usage is. If you want to look at the policing side, the Water Authority can look, are you watering your garden on a day that you're not meant to be watering it? And take action on that. So a rather critical infrastructure device can be extended from just looking at the burst water pipes.
And it is and interesting to look at with something like this is, well, we are looking at powering our electronic devices, and this is one of the solutions that we're looking at. But at the same time, for us to include something like that, that means we have to cut the pipe and then include one of these in the pipe, which will add costs to it. So currently we're kind of investigating the idea of, let's try to implement them when someone goes there to actually replace the pump, which is actually apparently, or replace the water meter, which apparently happens more than it needs to be. So that way we don't.
Water meters become inaccurate after about 5 to 10 years. So they have a policy of replacing them at fixed intervals. Now, interestingly, we could also add this into this particular device and look at the water meter reading from the meter itself and have a cross-check with this device to see if the water meter is actually accurate. Did you have a picture of the optical machine learning reading the meter itself?
No, but I'll look for it after we finish once we get into the questions. I'll find that. Okay, so there's another one of these devices. I think I found this one on Amazon, that just to see, because as Ian said, these are very popular and they provide different power levels for these type of devices. Like this one is very small, 12 volt, and there's this one that they offer it as like a picnic accessory, where you go to picnic, you put this in somewhere that's just where water is constantly running and you can charge your electronic devices, and kind of different specs of these devices that are available. And that's all of the little content that I wanted to cover for this particular presentation. So I'll stop sharing and get to your questions, and I'll look for that water solution that Ian was talking about. So feel free to ask us any questions you have.
It's also a good time, if you haven't had an answer to an email that you sent in, please let us know now. It just means it's been buried in the avalanche of emails that we get.
Hi guys. So I'll start my video. Quick question about the energy scavenging for shoes. I'm keen to know, is that something that was sufficient to meet the energy requirements of that solution, or did it have to recharge, or?
Yeah, it did, because that one that I showed you is just I found it on someone's blog. I've put the project name at the top of the slide, so I'll see if I can find the project link for that. But
sorry, I'm on my phone, so I couldn't actually see the slides particularly well. But I was fascinated by that, because that's actually directly relevant to something I'm doing at the moment.
So it's called Shoe Charger by Abel Haynes. So I think I found it.
Yeah,
I'll post a link for that. Yeah.
The problem and solution with these energy scavenging applications is generally they're only used to extend the life. So it's extremely rare you'll find something that will actually provide sufficient power to run any device. But instead of it lasting 8 hours, it might last 12 hours. Or instead of, so there's just that little top up. At this point, they're not efficient enough to really run devices.
Okay.
I posted a link to that project for anyone who's interested.
Yep, nice. I saw that, so thank you.
If you ever want to try it out, go onto Banggood or one of those other wholesaling type sites and get one of the shake torches. And these torches you're meant to be able to shake, and then they'll run for a couple of hours. And you'll find you'll spend 3 hours shaking it to get 15 minutes charge out of it. Right? They are not at the point where they're actually useful in most instances yet.
Okay, all right. So, okay, and I'll do some digging, because I said that came up in a discussion I was having yesterday. Almost exactly the same application sort of logic, but slightly different application. So
You'd probably find there are better ways to use a shoe to recharge a phone, but it'd be a bit more bulky. The trouble with that is, I think, Savash, it was piezoelectric.
Yeah, I think so.
Yeah. So when you run on piezo, you're talking voltage level might be all right, but it can't deliver any current. So that's a big problem with the piezo. If you use, say, an air cushion and blew that through one of those water turbine type things and generated from that, you'd probably find it to be much more efficient, but very bulky.
yeah, okay. All right, and then the difficulty then become like the entire soul, I suppose.
Sorry, I couldn't hear that.
So the difficulty then would become an insert rather than, it wouldn't become an insert, it'd become the entire soul.
Yeah.
So yeah, okay. Cool. Okay, thank you.
I'll just have a look at that too.
Just trying to find that digital water meter reader.
By the way, Ian, I did like your elephant story.
Oh,
It's a
yeah.
good one, isn't it? We'd like to keep elephants away from our campus.
Have you told your
Got-
horse mucus story yet, Ian?
We've got a few interesting ones like that. We've had some really strange projects over the years.
Well, a guy that I've been working with, actually catching up with again today's time, is Sri Lankan, so I'm going to tell him that story. He's actually very interested in putting some environmental growth monitoring tea plantations in Sri Lanka, which I think would be an interesting.
It is actually a really big problem in Sri Lanka. Because they destroy the crops, the villagers tend to run out and try and get the elephants away, and the elephants, of course, defend themselves. So being able to track them, and when they're approaching the villages, you send the foresters out or someone who's qualified to look after the elephants and move them back into their reserves.
Yeah.
There we go. Piezoelectric is shown to be a maximum of 2 milliwatts.
Right, okay.
But again, 40 milliamp hour battery, cell battery in 1 hour. So depending on your environment, you can extend the life out.
Yeah, okay.
But if you think about phones, they generally require a 2000 milliamp hour source to recharge them.
So yeah, this wasn't phones, this was something. This was an insole solution.
Yeah. So how's everyone else going? Oh, here it is. Oh, you got that one. Yeah, this is again on the water meter, and it's another way of reading the meter, because one of the big problems is when you've got standard meters like we have in Australia, you have to have a person go out and physically read the meter every so often to work out the water usage, and that is not efficient. So this guy made something up to read it and transmit the figure back using an AI recognition. There we go. So there's a water meter. That's pretty similar to the ones we use.
Yeah. And I
Yeah,
think this video is from DF Robots, so
yeah.
I think they've done a project. And there's I posted the link to this YouTube video in our chat, so if anyone wants to
I'd
check it out.
recommend DF Robots newsletter. They do come out with some really, really interesting projects and how-tos. They're a supplier of parts, so they're trying to sell you their goodies, but they do have some really useful stuff that comes out.
Anyone else? Any questions?
So I think next week we'll we've got a question. Yep.
Yep. Jean-Luc,
A
go ahead.
question. Okay, it's about the IMU.
Mhm.
I will explain what I have understood. IMU, you have got the three devices, accelerometer, gyroscope, magnetometer, and you
Mhm.
can find some that are separate, like the Arduino. We have got Adafruit. You have
Mhm.
got two sensors. They are
Yeah.
provided by NXP.
Mhm.
Or you could have, in fact, the sensors alone on it's called a module.
Yeah.
Here the BMX 160, we have
Mhm.
BMX 055, or you have something more clever. You have got the sensors plus a little MCU, the convex M4, doing all the computation for the fusion. So my question is about the fusion library. There's something called an XP fusion sensor. It's
Mhm.
open source, provided by Paul Stoffregen, and it does two things, the calibration and also the fusion itself.
Mhm.
I wonder if what are the sources which you know about the open source libraries for a fusion? And the second aspect, you notice that there is a drift. And this is very
Yeah.
annoying. And you
Mm.
notice that Xsense provided something better, most probably because they have got two things, better quality sensors and better algorithm. So what
Yeah.
information have you got about the library for the sensor, for the
Uh,
fusion? Sorry.
Sure. So, the ones that I found useful. So, what you mentioned there are two types of IMU you'd find. You find the standalone ones as you mentioned, where you have because the IMU itself, it doesn't matter whether the three different sensors are on the same chip or on different PCBs, right? It's the sensor fusion algorithm you end up using to get that orientation. And some IMUs like the Xsense or the new one that I've been looking at, there's one from Bosch, the BNO55 and the BNO85. They have that motion processor that does that fusion for you. And Bosch provides provides the libraries for it as well. I think one thing I would start when I'm kind of looking into these algorithms is first make sure they offer the sensor fuse data and the raw data at the same time, so we can validate their calculation. So I think the Bosch one, the algorithm that the Bosch one does, that looks promising to me. I've had a couple of students do projects with that one. We actually use the Bosch one for an indoor navigation project where we were doing Wi-Fi fingerprinting and using machine learning to determine where we are in a moving position, say in a single hallway. And we ended up using one of those Bosch ones to determine the orientation of the direction that we were moving because we didn't need it to be accurate. We just wanted to see roughly what direction we're moving on. I would say like algorithm wise, that's the best one that I know that recently come out that offers pretty accurate ones. But interestingly enough, if you look for IMUs, one of the more popular ones that kind of went out of life this year is the MPU 9250. And I think it's from Inverses. And lots of projects use that. And the libraries that are available for it are not accurate. There are some bugs in the library where, as you mentioned, the sensor fusion isn't that well done. But I can give you a couple. I think if you were to go with an IMU, like a standalone IMU, from the ones that I've seen, that BNO, the library for the BNO seems to be pretty good. But the other ones, I think you just have to investigate, validate whether they do actually
Yeah.
provide. a
Could
good
I just point
result.
out, I think there was
Mm.
mention a little bit earlier about the single chip and multiple chip IMUs.
Yeah.
When you've got multiple chip, depending on your application, it can actually have an effect. So if you imagine you've got your gyro here and your accelerometer here, and you spin around the accelerometer axis, your angular velocity on the gyro is quite different to the angular velocity you would get at the pivot point. Now, that would only have an effect in very high accuracy, small movement, but it's something to be aware of. And we've had problems with that when we tried to use a magnometer, which was separate to the gyro and accelerometer. So single chip solutions are generally better than having the items spread out.
One more thing I would bring up, we have a project student working on a kind of a quadcopter control, and with something like that, we sometimes have to kind of divide the magnetometer from the rest of them because the magnetic field from the battery of the device was affecting the magnetometer. So we ended up looking at a couple of solutions, and we saw that with most of the IMU solutions on the small hobbyist level quadcopters, they would take just the magnetometer slightly above, so it's further away from the battery. So there are situations where we would want them separated, but in most cases, as Ian mentioned, typically it works better if they're kind of embedded on the same plane.
You could have got around that by shielding it properly.
Yeah, true.
Thank you
Yes.
very
Okay,
much.
no worries.
A little precision, please, if I've got time. You mentioned
Sure.
the Bosch library. Do you mean the library which is installed on the computer? This is pop-up. We have got Bosch BMX05, I think, and we have got a Convex doing the computation. Is the library you are mentioning on the Convex? Is the firmware provided? Or do we have to have it separately?
No, I think I was just looking at the one that's provided on DF Robo. I'll let me just take a look and I'll post the link for that.
Thank you very much.
No
Okay.
worries.
I stay quiet now. Thank you very much for that.
No
Oh,
worries.
no, stay quiet. Talk as much as you like.
Yeah.
Okay. Well, it's finished in 7 minutes.
You might have already seen this, but this is the one that we managed to get to work. I've posted the link. This is for an Arduino. And then there's the... Oh, and one thing I would suggest everyone, when you're looking at working with a sensor, usually a good place to start would be to try to look for that sensors in one of these popular kind of sensor shops, like a DF Robo or a Core Electronics and things like that. Not to purchase it from there, because these sites usually provide resources in interacting with that sensor. So, for example, with the BNO88, from I think Core Electronics. Let's find it. But this is where I would typically get information as well. Like I would start with one of these sites, find the module, then start to see what sort of resources they provide. And especially, it's going to be more interesting when we get to the next seminar, because a good place to start would always be if we have a breakout board for a sensor with the PCB already provided, so you don't have to think too much about the circuitry that you would need to run that sensor. So let me see. Okay, this is just as an example, let me just bring up. So like this is a breakout board for an upgraded version of 9250. Now, if you look at the description, so we have a description here, like, but here you see we have libraries that if I open it up, which would bring us to like this is an Adafruit one, where they would have a description of the of the sensor. They would have all of the pinouts. So just to show an example. So this specific one, they offer I2C and SPI logic pins. So these are two different serial communications. And you see, they provide all of the different data sheets. Then when you go to their Arduino section, they would have circuitry for connecting that device to an Arduino. They would have example codes. They'll tell you how you can download programs and things like that. So this is where I would typically start with any sensor that I get my hands on. I'll first try some of their typical codes. Because then ideally, when we want to actually get into programming them, you would try to get away from that Arduino environment so you can actually program it in something a bit more lower level. That would give you access to some of the registers. That would help you kind of write a better, more efficient code. But as prototyping, proofs of concept, it's always good to start with something like this because you can at least see whether this idea would functionally work. Then you can always optimize it.
Yeah, we'll talk more about that and
Yeah.
that towards commercialization chat that we have.
And I'll put this one. I like this is an interesting chip because 9250 was very popular, and since it was out of life, there are multiple breakout boards available for it for the next generation of it, which is the ICM 2948. So it'll be interesting. I don't think this one has a motion processor, but it would be an interesting one.